I'm back, and so in the previous segment we were talked about what diffraction was, and now we want to talk about who cares. So now that we've defined diffraction, how is it important to the astronomer? So if you recall, a reflecting telescope looks something like this, where you've got a barrel and then this back end here, that's going to be a concave mirror. And so light is going to come down the barrel and then it's going to be reflected off of this, and then it's supposed to go to some other secondary mirror that then sends it off over here where you're going to have some kind of detector. That's what we want to happen. But the problem is that this tube acts like a slit. So do you see that there's an opening to this tube, just like there's an opening to a door? And then when light goes through this opening, it can be diffracted. It can be bent because it's feeling the edges of the telescope. That's bad. All right, so let's take a look at this next slide here. So what diffraction does is it's going to spread out light. So the light from a star is going to be spread out and it's going to make it look blurry. So let's take a look at two stars in that picture over there that are nice stars with no diffraction. So that's what we want to happen. We want to be able to see two individual stars in our telescope. But because of the effects of diffraction, what happens is that this one gets a little bit blurry and this one gets blurry. And if the diffraction gets bad enough, these two things can get so blurry that they just look like one blob. So that means we haven't resolved the two stars into two individual things. So this is bad, this is good over here. So we really do not like the effects of diffraction because it's going to make the stars look blurry, it's going to blur them together, and then we can't make out individual stars. So what does that mean that we need to do? So if we go back to our original slide here, there's two ways of getting around this. If we don't like diffraction, we could either use what kind of wavelength? You got a 50-50 shot. Do you want to use a large wavelength or a small wavelength? We don't like diffraction. We want to keep the angle as small as possible. So we need to use small wavelengths of light. Radio waves are horrible. Radio waves have the largest wavelengths of any kind of light, so they diffract the most of all the different kinds of electromagnetic spectrum light. On the other hand, gamma rays would be diffracted the least because gamma rays have the smallest wavelengths. Visible light would be in between those two extremes. Okay, then what's the other thing we could do? Bigger is better. So the bigger the diameter of our telescope, notice the diameter is in the bottom part of the formula, that reduces diffraction. So you'll notice that radio telescopes are the size of a building. They might have an opening that is 20, 30, 100 feet in diameter. So those kinds of telescopes are very large in order to reduce the effects of diffraction. So here we go. If you want to reduce the effects of diffraction, should you use a large or a small wavelength of light? So you always want the angle to be as small as possible. Therefore, the wavelength should be as small as possible. What are some devices that astronomers attach to their telescopes? Well, the first one is called a photometer, which we've already mentioned. A photometer, so here's an example of a photometer, and it measures the brightness of the light. So this measures the apparent brightness of the light. It doesn't measure the actual brightness of the light because that's a number that doesn't change, but the apparent brightness depends on distance. So that if I took my photometer and I hold it right up to the bulb, it's going to give me a big number, but if I back it off, it's going to give me a smaller number. So this is measuring the apparent brightness of light. So this is a device that an astronomer would put on their telescope. Another thing that they're going to put on their telescope is one of these things. So this is going to be called a diffraction grating. And a diffraction grating, you can't see it, but there's a little piece of plastic in here that has thousands of lines on it. So here is the cardboard part, and then inside the cardboard is this piece of plastic that has thousands of lines on it. And then those lines, each one of the lines acts like a door that the light is going through, and so it is diffracted. But I just got saying diffraction is bad. Well, in this case, diffraction is good, because what it will do is it will take like white light, when it passes through one of those doorways, it will open up and it will spread the light into the rainbow of colors, Roy G. Biv. So that's the purpose of using a diffraction grating. So this is something that they would put on their telescopes so they can get the spectrum of the light given off by a star. A third thing that astronomers put on their telescopes is going to be called a charge coupling device. And so this is going to be a device that it photographs the star. Now, in the olden days, they used chemicals. And so they would put some chemicals onto a plate, and then light would hit the chemicals, and then it would give you an image of the star. Well, what a charge coupling device does is, let's say that this is the charge coupling device. It has thousands of little pixels on it, and each one of those little pixels is capable of photographing the image. So it gives you a much clearer image. It's almost instantaneous, as opposed to using chemicals, which could take up to hours for those chemicals to absorb the light and then change it into an image. So those are examples of things that are on a telescope. So let's take a break, and then when we come back, we're going to talk about problems with telescopes.